And then in 2D, the same situation arises. We have the linear equilibrium points. And in the last session, we saw two examples of nonlinear 2D differential equations. And I'll remind you that they're the deer-moose examples. Here's deer, excuse me, here's moose, and here's deer. And the differential equation here was d prime equals 3d minus m times d minus d squared, and m prime equals 2m minus 0.5 md minus m squared. And you remember what the equilibrium structure of this was. It's an equilibrium point here, there's an equilibrium point here, there's an equilibrium point here, and there's an equilibrium point there. 4 equilibrium points. And for this equation, with those parameter values, it turned out that this was the only stable equilibrium in the system. Unstable, 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 and everything goes to the stable equilibrium with some moose and some deer. On the other hand, when we just changed a parameter, we doubled the interspecies competition term. We made interspecies competition a little harsher by making this a 2 and making that a 1, just doubling them. Then in that case, the second deer-moose model, as we call it, we had M and D, and again we had 4 equilibrium points, but now the stability had changed. And now we have this very interesting situation in which this is stable, this is stable, this is unstable, and this is a saddle point. And the saddle point has an outgoing direction, and it has an incoming direction. And then if you ask what is the shape of the trajectories in this second deer-moose model, the answer is they look like this. In other words, everything goes to this stable equilibrium or this stable equilibrium. The saddle point is unstable, the 0, 0 is unstable. So the key principle which you see here is, again, all equilibrium points are linear equilibrium points, saddles, whatever. And what a nonlinear system does is it puts several multiple equilibrium points in the same system. Now, the minute you have several equilibrium points in a system like that one, you have a very interesting possibility arises. So if I were to ask you, here's a random point right here. If that's the initial condition, where does the trajectory go? And the answer is there are two possible places it can go to. Where does any trajectory go? It goes to a stable equilibrium. So this trajectory over here is going to go to this stable equilibrium, but this trajectory over here is going to go to this other stable equilibrium. So we have multiple equilibria, so to speak, competing against each other. And the answer to the question, given a random initial condition, where will it go, is that there's a little dotted line here, as it were. And if you are on the south side of that dotted line, you are going to this equilibrium point. And if you're on the north side of the line, you're going to go to this equilibrium point. And this line, by the way, is the 1, 1 line of D equals M. So what this says is there are two different regimes, and where you go depends upon your initial condition. Now, there's a language, there's a certain word that I want to now define, which is used in this discussion. And it's the word basin. The basin of an equilibrium point is the set of all points that go to the equilibrium point as time goes on. So the basin of this equilibrium point is everything north of this line. That whole blue sector there is all going to that equilibrium point. Whereas south of that line, the basin is everything that is going to that equilibrium point. So state space is quilted, if you will, into two big regions, the basin of this equilibrium point and the basin of that equilibrium point. And that is going to be typical of a bistable system, as this is. By the way, if you're wondering where the word basin comes from, it comes from geology, like the basin of a river. If you think about North America or the United States, draw a little horrible map of the United States. The U.S., for those of you who are new to the U.S., the United States geologically and hydrologically is divided into two huge river systems. The first river system is the Mississippi River and the Missouri and all the tributaries of the Mississippi. And the Mississippi River flows into the Gulf of Mexico. And the other that's the eastern Great River system. And the western Great River system is the river system of the Colorado River, which flows down into the Gulf of California. This is Baja California, and that's Mexico. Excuse me, that's Texas. Texas and going into Mexico. And here, this empties into here. Now, in between those two river systems, there is a ridge line. And that ridge line is called the Rocky Mountains. And in particular, the crest line of the Rocky Mountains, which runs roughly through Denver, is called the Continental Divide. And theoretically, a drop of water just west of the Continental Divide will find its way into the Colorado River system and into the Gulf of California. Whereas a drop of water a little bit to the east of the Continental Divide will find its way into the Mississippi and go down the Mississippi down to New Orleans. So the Continental Divide is an unstable equilibrium point. These two are stable equilibrium points. And so here is the unstable equilibrium point and the stable equilibrium points. And so we have in the geology, we have a stable, unstable, stable. And that forms a 2 equilibrium point system, and the Continental Divide divides the United States into 2 great basins, the Colorado Basin and the Mississippi River Basin. So using the concept of basins and stable and unstable equilibrium points, we can now make a major definition. And the definition is of the word switch. What is a switch? Well, I'm going to define it. I'm going to define a switch as exactly what we just saw, as an unstable equilibrium point that is flanked by 2 stable equilibrium points. And why do I call that a switch? Well, think about a switch on the wall, at least one of the old-fashioned ones that you flipped up and down. Let me just turn that vertically and make it unstable, stable, stable. This is your wall switch. It has a stable equilibrium called on. It has another stable equilibrium called off. And in between those two, and you can try to get the switch knob to stay at that point, but you can't because it's unstable. It's either going to snap back to the on position, or if you go just past it, it's going to snap to the off position. So a switch, in particular a biological switch, is always going to be associated with this geometry: stable, unstable, stable. And this is also true of biological switches. And we hear a lot of talk in biology about biological switches. For example, the switch that turns on gene expression, the switch that turns on hormone production. And another example, which I'm about to develop, switching on of the gene expression for some function. But in every case, when you hear the word switch, this is what you are going to see, and this is how a biological switch works.